first speaker of this session is Endre Csoka from Hungary, from Alfred Brainy Institute. As many of Hungarian people are from this place, beautiful place. He will speak about limit theory for combinatorial problems.
Thank you very much. Okay, so now I'm going to tell you a new proof technique for combinatorial problems through three different problems. If you don't like these problems, it's fine, because we concentrate not on these questions but the proof tool. So the very first one is the following question. It's a two-player game between hider and the searcher. The hider caches k golds in n potential holes, and they have the hider has a total digging time 1, and the searcher has a digging time h spent for finding these golds, and if he finds at least j out of the k, then he wins, otherwise hider wins. Is the problem clear? We will see some examples. So this is a two-player zero-sum game, therefore what you should know about it is that there is an optimal hiding strategy, an optimal searching strategy. The hiding strategy guarantees some probability of winning. The optimal searching strategy also guarantees some probability of winning, which sums up to 1. So it has such a nice kind of solution. That's the only thing what you should know about the theory of these two-player zero-sum games. So we focus on k equals j equals 2. So there are two golds, and both golds should be found. This is the simplest non-trivial case, and it was solved up to 4 holes. And just in order to understand what the problem is, let us see a few examples. So here you have 4 potential holes, and the hider has a unit of time to hide both nuts, and the searcher wants to find both. Okay, if the hider has less than 1 unit of time, then what's the optimal solution for hider? Put to the bottom of, say, both nuts in the bottom of one nut, and the other one cannot find it, so it has a probability of 0. If it's more than 1, then the searcher definitely has a probability of 1/10. Why? Because there are 10 possible different options where to catch the 2 nuts. Either both nuts in the same hole or 2 different holes. There are 10 possible options. I make a guess that, for example, I guess that one is here, one is here. I'm digging here until the first nut, then I continue this way. And if my guess was right, then I find these nuts. On the other hand, if the hider puts chooses also the 2 nuts, the placement of the 2 nuts uniformly at random, and if he uses depths 1/2, 1/2, or if it's the same hole, then 1/2 and 1, then the searcher cannot find it in more than 1 cases if he doesn't have 3/2 digging time.
What do you mean 1/2 and 1? Would the squirrel put the nut 1/2 down and hold? If he goes further, surely not.
Yes. That's the. So in the second case, here.
In the same hole?
Yes, there's a possibility that he puts this 2 nuts in the same hole at depth 1/2 and 1, because if you find 1 nut at depth 1/2, then you will have no clue whether the other one is still here or in any other place, it turns out to be that this is the optimal strategy. And later on, the strategies become more and more difficult, but all of them has this kind of structure. There are finite possibility of hiding points. Choose one, and the searcher has some strategy which guarantees.
So your squirrel may hide 5 nuts in the same hole at different heights?
Yes, it's possible, yes. And it can be an optimal strategy. But now we are focusing on nuts or holes, depending on what you prefer. Okay, so it was solved up to 4 holes. This was the picture, and it just showed a very chaotic picture. This is the same shown as in a graph, so one would expect that it has no nice structure. We may try to solve it for n equals 5 or 6, which is even more and more difficult, and we won't see any more interesting things. It turns out that this is not the case at all, and I'm just showing you. Okay, so just a test for you first, whether you understand the things. Here is a lemma that the hider always uses placement which completely uses his digging time, say for 1/2. It doesn't does everything like 1/4 and 1/4. Why is it true? Sorry?
You can't ask such a simple question.
Why? Okay, well, what's the answer?
Because what difference does it make if you go even further down?
Okay, do you agree that this answers the question? So if you so say put it in depth 1/4, and it's not a good idea because caching it at bigger depths is always better to the hider. This proof is wrong.
Yes, that's interesting.
This proof is wrong because if you find something here, then you know that the other one can be anywhere at depths at most 3/4. But if you find it here, then the searcher gets more information, and this is why this proof is not true. Not even the lemma is true.
That is interesting.
And what is even more interesting is the technique how I found this result. Okay, so just a little definition. We define the extremal game when the hider is forced to choose a placement which completely uses his digging time, and technically we will prove that this lemma is false, so that we will show that with some parameters the extremal and the non-extremal games has a different winning probabilities. Okay, so the trick is first we consider the case when n tends to infinity. What do I mean n tends to infinity? So there are infinitely many holes. If there are infinitely many holes, so then it's hard to define how to define the limit of these games, because if you have a countably infinite number of holes, then it's difficult to measure the proportion of the holes what you cache. So if you model the lot of holes as an interval, then you cannot choose a uniform random permutation on the holes, which was necessary for the strategies. So it's a non-trivial task how to define it, but here is a nice definition, maybe the following. So first, we should see that if the hider is forced to choose uniform permutation on the holes, And the searcher is also forced to use a random permutation on his strategy, but it doesn't change the value of the game. And after this, the limit game is defined in the following way. The hider chooses two depths. Two x-coordinates are chosen at random. These are chosen by the hider. These are chosen at random. These are the placements, and the searcher doesn't see this, but he a digging plan, a monotonic digging plan in which so that the integral of the total what he digs must be at most 1. And at a point, if he finds a nut, then he can then this part is fixed, but he can revise the further plan of caching, of digging, and so this defines a two-player game. And the reason why I call this limit game is that we can actually prove the convergence, that the values of the finite games converge to the value of this limit game, because you can convert a strategy in a finite game with a large n to a strategy in the limit game by just splitting it into n parts and use functions like this. This is a conversion from the finite game of a searching strategy in the finite game to the limit game. Similar thing works in the other direction, and so this is the point, the message of the entire talk, that if you want to understand what happens if some parameters tend to infinity, you shouldn't just change the parameter to infinity and looking for a meaningful problem, but what you have to look for is a game which may look differently from the original one, but you have a convergence of this kind. We have this convergence about the winning probabilities, not about the strategies, but this is already fine to me. It will be enough for us. Okay. So here we have a finite length interval, and a hider had the searcher had a unit of area which to dig, but it turns out that if this the length of this interval is larger and larger, then the searcher strategy doesn't really change, because it doesn't really use too many holes, so it also converges to something when this interval tends to the infinity. And in order to define this problem, now of course if it tends to infinity, then the probability of finding both nuts or golds that tends to 0, but you can normalize it in such a way to get a meaningful problem. And in this case, the way to define the problem is the following. The hider chooses two depths, and the searcher declares a searching strategy, and we consider the two-dimensional measures of x, y, and x2 of these pairs for which the searcher would win. And this is what the searcher wants to maximize and the hider wants to minimize. And again, this is the double limit game, and we again have this theorem that the values of the finite game converge to the value of this double limit game with some normalization factor. Now, why is this double limit game interesting? The reason is that we have no more parameters. So we had a two-parameter problem, two integral parameters. Now you have just one problem, no parameters. If you understand this only problem, then you already got to know a lot from the entire two-parameter problem. And what we are going to prove is that the values of the extremal and the non-extremal double. So when I started to analyze this, I understood something about how the solution looks like. And what was strange in the original game, that this false lemma, that this is false, turned out to be quite clear in the limit. So the way to prove it is, so first we prove that the two games, extremal and non-extremal games, have different values, different winning probabilities, and therefore, due to the convergence, it means that there are finite parameters for which these values are different because they converge to different values. So after a while, they must be different. And if the values are different, then it also implies that it can only happen if the hider uses depth summing up less than 1 with positive probability. So just this is the key thing to prove, and the proof is the following: if the searcher digs and finds a nut in the extremal game, if it finds a nut at depth y, what should he do next? So the question. Extremal game, so one nut is at depth y, the other one is at depth 1 minus y. How you should continue the searching? So you found something here, extremal game, the other nut is at this depth. You want to maximize the measure of the cases when you find it. So you should continue by digging this part with the largest possible interval. Or also if this was what you did before, this part, then you extend it this way so that the integral must be 1. That's the best you can do next. And in the extremal game, we know that this is what the searcher should do. Any optimal searching strategy should do this. And if we assume by contradiction that the extremal and the non-extremal games have the same value, then it means that optimal searching strategy in the original game is an optimal searching strategy in the extremal game as well, because the values are just the same. And it means that the optimal searching strategy in the original game also has this property. So assuming that the two games have the same values, any searching strategy of the original game is optimal in the extremal game as well, and any searching strategy in the extremal game has this form. And this means that in the original game, the searching strategy has this property, but if the hider hides two nuts roughly at depth 1/4, then it means that after the searcher finds the first nut. If he plays with optimal strategy, then he should continue this way, looking for the largest possible interval at depth 3/4. And it turns out to be a very ineffective searching strategy, and by considering some specific strategies, it turns out that to be impossible, that such a strategy can be optimal. We can show a better strategy than any strategy with this property. This is a contradiction, so we have an existence proof that that the extremal and non-extremal games are different, so the values are different, and therefore the finite games are different. So this is essentially the story, and this was just much more than an asymptotic analysis. If you try to transform this proof to a classical asymptotic analysis argument, you will find that it's almost impossible. Always possible, but you would give up if you try it. So, so it's really something to do about limit theory. And just after this result, we had these results. I was able to find the solution first of the double limit game, which is surprisingly the following: choose the depths y1 and y2 uniformly at random from this triangle. So, you know, both depths should be non-negative and the sum should be at most 1. This is a triangle. We choose a uniform random point, and that's the hiding. These are the hiding depths, and this turns out to be optimal, and you can easily find an optimal searching strategy which provides the same value. Based on and after the double limit game was solved, you could transform this solution for the original game, and it's not completely solved, but it's mostly solved. So originally we started from a completely chaotic picture. It seemed to be hopeless, and now we are not ready, but very close to be ready after these arguments. Okay, so this was one of the 3 stories I wanted to tell. Do you have a question about this story?
For more gold pieces,
yes, if you have not only 2 golds, but k golds, and all k should be found, then the solution is the very same. You should find the uniform random point from the corresponding simplex, and this turns out to be optimal if h is larger than something and less than n over k, but in most of in a very big part of the possible parameters, this is the optimal solution. Also, we have something if j, the number of nuts to find, is 1 less than k, then in this case it should be equation, so you use only extremal ones, but uniformly at random among all, and we don't know anything about the other cases, and it's true only for some parameters. So it seems that this strange thing that lemma was false happens only if k and j are equal.
for half it's not true.
Most probably it's not true, just only if you have to find all of them. Okay, so you can wake up, it's a simpler and shorter story, on the other hand with weaker results, but you can join if you were lost before. The next problem is the Mannekar-Miklós Singhi conjecture, which is the following. You have two values, n and k, and you have to find n values summing up to 0, and real values, so that the probability that k values chosen uniformly out of these n values sums up to a positive number. So the question is how to choose these n values so as to maximize this probability. So for example, if you have 1 million, n is 1 million, k is 100, what would you do? Any guess if you didn't know it before? N equals 1 million, k equals 100. If you have louder, please, because I'm waiting for any answer.
Put one that is very negative and the rest is like...
Yes, true, absolutely. You choose one negative, all the others are positive, and you have a negative sum only if you choose that one negative value. In all the other cases, the sum will be positive. And the conjecture is that if k is at most the quarter of n, then this is still the optimal solution. And a lot of attention was made to these questions, but still, this epsilon here is extremely low, so we only have a very few results about it.
You left the Misha-Chomkin reference, which prompted the Sudatov paper. They read the Misha-Chomkin paper and they continued it.
Okay.
So he was the one who started it. So he's the one who is missing.
Okay, thank you, I will correct it.
Because Deju took mention the problem in Cambridge to a student. And that's when Misha-Chomkin started working.
Yes. So Endre Miklós is here in the second row. So we all again analyze this question, by the limit theory tools, we define the limit problem when n tends to infinity. What do we mean the limit problem? It's again something non-trivial, because okay, there is infinitely many numbers, but how to choose k out of them at random, or what do we mean? The form of this conjecture suggests that the proportion of k to n should be something fixed. But in this case, how to define it? One thing is that, okay, if there are too many elements, that the events that two different elements are chosen are essentially independent. Okay, that's one thing. But the other thing is, you have this sequence. What should be the limit of this sequence? You cannot say that minus infinity and a lot of ones, or you don't have this 1 over infinity or constant over infinity. So this sequence has no correspondent one in the limit. But we can resolve this problem by considering first an equivalent problem, which is the following. We don't have the okay, so sorry, I changed the slide in a wrong way. So quite recently I made a illustrate in my slides. The trick is the following. You don't have this assumption that the sum of AIs are 0. This was our assumption, but instead of this, we just consider the probability that sum of AI xi is larger than the expected value. So, you know, if you add a constant... This?
Yeah.
So if instead of having this condition, that they sum up to 0, we change this to the expected value, then we have an equivalent problem. And why is it useful? Because in this case you could say, you could replace this construction to -1, 0, 0, 0, 0, and so on. And you can define a limit of this solution by -1 and infinitely many zeros. Sorry, this problem is written badly. No, okay, maybe not. So, the limit problem is that we have this p, and we have to find these values so that the sum of their squares must be finite. Otherwise, you can come up. And you will have an extra term that if you have a lot of small elements so that they tend to 0, but the sum of the squares doesn't tend to 0, then it just converges to a normal distribution of the effect. And in the limit you should think about this as well. So in the limit problem you have values and these, so that b times a standard normal distribution plus the difference from the expected value. Xi is an indicator variable with probability p, should be positive. So this is the limit problem for which we can again prove this convergence, that if we have n and k large, n tends to infinity, this ratio tends to p, then essentially these values tends to the optimal probability of this limit problem. We have one parameter less, we only need to... Yes, and the strategy space is a compact space in this sense. It's fine if you don't understand it. It's just technicality, and the reason why we had this limiting thing is that we have this. So the main tool of this convergence is a version of the central limit theorem. This is what allows us to define limit problems. Okay, so this is again the limit problem, and the conjecture is that depending on the probability, this is the optimal curve of so the best probability you can achieve. Where does it come from? This is just the maximum of some different strategies. This is what was mentioned in the Manikan-Miklós-Szinghi conjecture, that if this probability is low, or the k over n is low, then the best thing to do is choose one negative, all the others are positive, and that's the best solution. If you are close to 1/3 and below 1/3, then the best thing is to choose 3 positive values, all the others are negative, or in the limit game 1, 1, 1, all the others are 0. And if you choose this one, then you are average, and it has a higher value, and so on. These are for 2 or 5 above and below, and this is 2 positive values. And just there are some other things. So if you choose not 1, 2, 3 or 5 but 4 or any other values, these provide lower probabilities, and from this we can make this conjecture that in the limit game the optimal strategy is just this, that you have 1, 2, 3 or 5 plus 1s or minus 1s, all the others are 0, and from this you can pull this conjecture back to the original game, original problem, that this is the structure of the original question. And yes, and sorry, and this is what we could learn from limit theory here. So originally the conjecture said nothing about larger k's, and just that k, if k is at most n over 4, then that strategy is optimal. Now we have extended this conjecture for every k and n, and also we believe that the original conjecture, which had the threshold 1 quarter, is in fact here something around 0.32. So we got closer to understand the entire problem, and also so probably solving this limit problem is easier than solving the original problem, because you can avoid a lot of ugly rounding problem due to having integers, and it's easy to believe that once you can solve the limit problem, you can somehow convert it to solving the original problem as well. So that was the second story. Do you have any question about it? Yes?
So far you didn't progress on the original conjecture. So.
No, yes, it's true. It's true. This story didn't make progress on it. It's just we just offered a simpler problem to solve, and also we managed to generalize the original conjecture. And the third story is the following. So the story is the following. In my censored version, your mother-in-law is ill, and she doesn't want to take the drugs which would save her life, but you can cheat her, because she will come for you to take cake cookies out of N, and you can hide some drugs to the different cookies, and she will choose at random, and if he consumes at least more than the amount of these drugs, then we can save her life. And how to maximize the probability of it. The question was asked in a very similar version by these two guys. And the conjecture was that no matter what the parameters are, the optimal solution always looks like the following. You should choose a number of cookies and put the same amount of drugs to each of them, and you don't put anything to the other cookies. So in this abstract version, you have a number summing up to 1. Choose these values, non-negative values, so as to maximize the probability that k, a random k out of them is sums up to more than d. Okay, first notice that if this critical d is just k over m, then it's equivalent to the previous problem, because you just measure the difference from 1 over m, and you just consider the ai minus 1 over m, and it will be the very same program. So this is a generalization of the previous program. And the optimal value of s, they just try to understand, and it would be important to understand what this s is depending on the parameters, and by some computer calculation they found that it seems completely chaotic. We don't know what this s can be or can't be, and what we will now doing, what I did about it is I made the full description of S, so it seemed to be chaotic, but it has a finite complexity, and we can understand if we define and understand the limit problems again. Okay, so we had one limit problem. This was the Monika-Miklós-Szigli problem. But what if this critical dose is significantly larger than p, it's a larger constant, then and n is large, so k over n is p, n is large, and the critical dose is much larger than this probability, then that's one problem to consider. Just realize that the solution of the conjecture solution of the MMS problem, that you choose one negative, all the others are positive, is not good in this case, because it just means that S equals n minus 1. You don't put the drug to one cookie, put equal amounts to all. In this case, you cannot gain much more than the expected value. And if the critical dose is much higher, then it's no longer good. Another interesting case, if the critical dose is just a little bit larger than this ratio in a scale 1 over n, or this is the boundary between, then the difference still tends to 0, but the difference is more than constant per n, the constant divided by n. And understanding this, so this is the intermediate case when so if the difference tends to 0, but it's more than 1 over n, then you can no longer use these negative values, because it doesn't help to increase the expected amount from k over n to k over n minus constant. You have a little bit more, but anything significantly more is enough. In this case, the limit problem will look like the following. It's the very same as the original MMS problem, except that you cannot use negative values. I'm about to finish, yes? And this is what how the picture looks like. So it shows such a picture. Another limit gain when it's just a little bit above this. It's described by this nice colorful picture. And in total, finally, what we get is that we can get a description that S is one of these lot but still finite number of possible values, and always one of them is optimal, and there are, and it was easy to find other possible counterexamples which were almost counterexamples, so it just helped to understand the entire problem. So that was the third story as well, and just this is the summary of that. What I was speaking about is that the message is that you should, if you want to understand discrete problems, find interesting limit problems, try to solve this, and you can get some conclusion to the original problem from the solution of the limit problem. So thank you.
I think we have time for one question or comment.
And how is your finite approximation? You have, in the limit, you know what happens, and how fast is the convergence?
This is always a difficult question, because any time when you have this argument, it's just always easier to prove existence than exact bounds. It's possible I didn't do this calculation, I didn't feel it very important, but
Is the calculation? I mean, in theory, can you do it?
in theory I can do it, but it's not very obvious.
You can do it in an hour.
Not in an hour, in a week.
No, but is the theory done? I mean, do you know how fast is it? Like
Now I'm
1 over n squared or what?
Generally no, and especially for the first problem, it's incredibly hard to transform this argument to a classical
So is the
argument.
convergence logarithmic, polynomial, exponential?
Didn't even think about this.
No, but then it's not a calculation. That's a result. That would be a result.
Yes, but the entire point is that, for example, if you think about the first problem, I didn't do this calculation and I didn't need it. I was able to answer the original problem without knowing anything about how fast it converges. And that's the typical plan to do. So,
Isn't
yes, so the
what the value is given n and h, what the value is? I mean, given the parameters, what is the value? That's the problem. So you say you have answered it, but you don't know, you didn't bother to work it out. So
I mean, it turned out that from a small constant, the solutions are the very same for some other parameters, but it didn't follow your way that I give bounds first, that how close its convergence.
I'm not suggesting that at all. I would not in 1,000 years would I suggest that stupid way of doing it.
Okay.
Okay, let us send the speaker once again.